So we made our first input file. We ran it in Nastran, and now we need to look at the results. So again, I always want to stress in this class that when you do a problem, you need to validate it somehow. The problems in this class are simple enough that almost all of them have exact solutions. So here's just the mechanics of materials type of solution for this problem. So it's just a statically indeterminate problem. So we have reaction forces at A and B. They sum to equal the 5 kip force. But it's statically indeterminate. You have two unknowns, one equation of equilibrium. So you have to use the supplemental compatibility equation that the total elongation of this specimen is 0. So here's the elongation of the first part, and then here's the elongation of the second section. The sum of the two of those has to go to 0. That gives you this relationship in terms of the reaction forces. Allows us to solve for the reaction forces. And then once you know the reaction forces, you can go get the internal forces and then the stresses in each one of those sections. So here's this compressional 15 ksi stress in this one, and an extensional 10 ksi stress in this element. Then we can get the displacements of the nodes. Obviously, these nodes displace 0, but this node displaces 7/1000ths of an inch to the left. And then we can get this strains. And here the strains in the elements. So these are going to correspond to the stresses and the strains in the elements. We'll be able to get the reaction forces from the SPC reactions. We'll be able to compare those. And of course, we can compare the nodal displacements. We can check all those against our finite element results. Okay? Okay. Let's go back to the slides. And let's show you the output files. So let's talk a little bit about output files. So in Nastran, you have several output files. And depending upon what output sections you put in your load case, you might get some different ones. The main one we're going to consider in this class is the .FO6. It's an ASCII file, and it outputs the data, the results. Typically, you get the log file that tells you what's being executed. The FO4 gives you ideas about how much memory is being used in the solution. Sometimes you write what are so-called punch files. We might talk about that. Those can be read by HyperMesh. They're also ASCII file or text files, so HyperMesh likes to read those. If you have lots of elements, millions of elements, these files can become really large. And in fact, a better format to output are binary files. They don't take up nearly as much space as an ASCII file. So the OP2 file is Nastran's binary output file. But in this class, we won't have anything any more than maybe 100 elements tops. So the ASCII files are fine. Okay, the FO6 is the main file we're going to look at. You can open this up in a text editor like Notepad again. It's an ASCII file. It's in sections. Actually, those sections are called pages. Why don't we open it up now, actually, just to look at it, so you can see what it looks like. So here's the FO6, and I think if I double-click on it, it'll open right up. All right, so here's my FO6 file. It's, again, text. The pages are kind of denoted here. You can see on the right side, you've got page 1, 2, 3, so on and so forth. So let's talk about the format of this. Here, results, so on and so forth. So if you get it to run, open up this file and you can follow along with what's going on here. The first page is like 120 lines, and that's just a bunch of Nastran PR. You can ignore that. Page 2 spits out some of the comments that you put in up top. The third page gives you the executive case summary that tells you what solvers you use. In this case, it'll be solver 101. Again, that's really not of much use for the most part. The fourth page gives you the load case summary. Again, that's not bad to look at, just to make sure that it's running the load cases you think it's running. Page 5 gives you model summary stuff like number of nodes, number of elements, number of loads, so on and so forth. Pages 6 through 9 give you a summary of how the solution went. We won't talk too much about this, but one of the big things that introduce error into finite element problems are so-called matrix conditioning issues. And if your matrix is poorly conditioned, maybe you have inappropriate boundary conditions or highly distorted elements, they're going to result in element conditioning problems. And if the conditioning is really poor, it will not solve, or it'll give you errors in the solve. So looking at 9 through 6 will give an indication of how good the linear solve was, and if you have any conditioning problems. Again, we'll talk about a little bit of that in Chapter 5, I believe. But really, that's summary stuff. So after those, we get to the results. So here we start with page 10. This is the output from page 10. This gives you the displacement results. Here you can see the displacements. This is the actual output from our .fo6 file for this run. For each grid point defined, it gives you the nodal displacements and the nodal rotations. So T1, 2, and 3, those columns are the translations in the x, y, and z direction. And then R1, 2, and 3 are the rotations about the x, y, and z axes. And again, if you specified another coordinate system, CID, for that particular grid point, it will resolve these displacements in that coordinate system. If you leave that blank, it's going to use global, and these are in the global x, y, z axes. Okay. If you have multiple load cases, there will be different displacements typically for each load case, and so it'll have the displacement for each load case or subcase listed separately. Here we just have one subcase, so you can see it just shows the displacements for the 3 nodes for the one subcase. Okay, so here you can look at the displacements. All right. In fact, here you can see all the displacements are 0 except for the x displacement at node 2, and it's minus 0.00737 units, and that actually corresponds directly to the exact solution. If we go back to the exact solution, where's the exact solution? Here's the exact solution. You can see the displacement is minus 0.00763 inches. Okay, so this is why you want to check those values. All the other displacements are 0. Okay. The next section gives you the SPC constraint data. So these are the reaction forces. So obviously, if you have a constraint, say we're fixed at the ends, there are reaction forces that enforce that constraint. Those are the reaction forces R and B that we solve for in the exact solution. Okay. You can also have reaction moments. Okay, so it's built in. So you've constrained 6 degrees of freedom, so you can have reactions, forces, and moments about those 6 degrees of freedom. So here we've constrained 2 nodes, 1 and 3, and here it's giving you the reaction forces. Okay, you can see the moments are all 0. The only non-zero reaction forces are in the x direction, and this says that we have a 3.6 kip force at node 1, and then a 1.3 kip force at node 2 in the x direction. And that also corresponds to the exact solution. Go back to the exact solution. This is posted on Blackboard as well. You can see here the reaction forces. 3.68 and 1.31. Okay. 3.68, 1.31. So it matches exactly. All right. Next section, this is page 12, gives you the element strains, because we asked it to write it out. If you leave that element strain section, if you leave this part here where it says strain von Mises equals all, then it won't write out the strain data. But we're going to ask for that, so it gives you the strain data. The form of the element strains depends upon the elements being used, whether it's a C-rod, C-bar, C-hexa, or C-tri, or whatever. Because the elements are formed differently, they can support different types of strain components. For a bar element, you have axial and torsional strain. That's the only thing it can support. It can't support bending, so either it has the stretching strain, you know, like you're pulling on the rod, and then the torsional, like you're twisting it. All right. So these are going to be resolved in the local element coordinate system. So when it says axial strain, that's the actual strain in element 1 down its axis. And you can see here, for element 1, that's the first sort of column, it has a compressional strain of 1.7 KSI and a torsional strain of 0. All right? If in your material card you specify a yield, that it can give you a safety margin, but we didn't do that, so it leaves this safety margin. It's like a factor of safety at 0. And then you can see in the right half side, we have the strains for element 2. It's a tensile strain of normal strain of 1 times 10 to the minus third. Okay, and again, those correspond pretty close to the exact solution. Then we also have the stresses in the FO6 file, and this basically has the same form as the element strains. It's just obviously the stresses. Okay, you get axial stress, torsional stress. The axial stress in the first element is minus 1.47 KSI, and then its tension in the second element, 1.052. And again, you can see that that corresponds to the exact solution here, right? 14 KSI and 10 KSI, right? All right, 10 to the fourth, 14 minus 14 KSI, 10 KSI. And again, also with the strains, if you have multiple subcases or load cases, it'll write the element stresses for each load case. Okay? Well, that's pretty much it. So that shows you the results. I suggest that you actually go through this stuff yourself. Try to write the input file by hand. I mean, I posted the input file online, but, you know, you can use that as a reference, but I suggest that you actually write your own input file so you get used to the formatting and making sure that all the values sit in the right field widths. Run it. Look at your .fo6 file. Make sure that the values correspond to the values here or the exact solution. Okay. You can use my exact solution if you want, but look through it. That's fine. For your homeworks, when you do computational problems, you will always have to justify your finite element results somehow, either by solving the exact solution by hand or maybe a bound type of thing, or looking at convergence, or some way of showing that the results are reasonable. Okay? Okay, well, that's pretty much it. Again, also I recommend looking through the Nastran file, this Nastran reference manual, the linear static user's guide. Whenever you go to start doing these homeworks and developing these Nastran files, always have this open. It's a big help. Especially we'll be looking mostly at, the Nastran element section, and then that's where you'll be most of the time. If you're doing 2D elements, you might look at the C quad 4 elements and the C tri 3 elements, and look at the sections here. Okay, you can see these are actually the forms of the inputs. All right. Okay, that's pretty much it then. Well, good luck, and I guess the last thing I should say is don't get frustrated. It is a little tedious at first, but I find that it's the most important skill you learn out of this class really is the ability to be able to look at a text finite element input file and be able to directly deal with what's being done in your finite element model, as opposed to having a graphical preprocessor kind of interpret what you want done, and not being sure exactly what's being solved is what you want to be solved. Okay? Okay, thanks.